Developing a single orbital rocket engine can consume more than $100 million before the first flight even leaves the launch pad. To survive this extreme capital drain, a space startup must manage a maze of government contracts, venture capital rounds, corporate taxes, and unexpected compliance fees that average $70,000 per launch license. A hidden operational decision, rather than the price of raw steel or liquid propellant, routinely bankrupts rocket companies before they ever reach the launching pad. The romantic vision of the commercial space race features billionaire founders celebrating orbital arrivals on live broadcasts. This polished exterior makes the space sector look like the ultimate playground for generational wealth. Entrepreneurs view orbital launch as the gatekeeper to a $1 trillion space economy built on global communications and orbital observation. They imagine building a fleet of rockets that carry satellites into orbit for $10 million a flight and returning to Earth to be reused the next week. In this fantasy, the launch pads are always clear, and the weather is always cooperative. The financial reality is a brutal combat zone where engineering physics meets extreme logistics. The path to orbit begins with a mountain of physical infrastructure that cannot be bought off the shelf. Before building the first rocket, a founder must secure land for research, manufacturing, component assembly, and testing. Leasing a decommissioned military launch pad or purchasing remote land for engine tests can cost between $5 million and $15 million. Building a single heavy test stand with concrete flame deflectors and high-speed sensor arrays requires another $8 million. This testing site must be far from residential areas to comply with noise regulations, meaning the company must pay to build private access roads and run electricity grids into the wilderness. For small launch companies, constructing a launch pad from scratch is a massive engineering hurdle. They must install propellant storage tanks, liquid oxygen pumps, helium pressurization systems, and umbilical towers. Building this ground infrastructure can easily consume $50 million before a single rocket is erected. Ground support equipment includes the propellant storage farms, the umbilical towers, the launch mounts, and the water deluge systems that protect the pad from the rocket engine's acoustic energy. A water deluge system must dump over 100,000 gallons of water onto the pad in less than 30 seconds during ignition. Building this water storage tank and high-pressure pumping system costs over $3 million. Rocket engines are tested by securing them to these massive metal frames and firing them at full thrust for several minutes. If the mixture of fuel and oxidizer is slightly off during ignition, the engine experiences a catastrophic failure known as a hard start. A single hard start can vaporize the engine, destroy the concrete test stand, shred the telemetry wiring, and wipe out 12 months of engineering work in a single second. To prevent this, startups must purchase specialized testing equipment, including flow meters that can measure supercooled liquids at thousands of gallons per minute. Designing the turbopumps that feed these engines is the most difficult task for any propulsion engineer. A turbopump must spin at over 40,000 revolutions per minute while handling cryogenically chilled liquid oxygen on one side and burning kerosene on the other. A single seal failure inside the pump can mix these fluids, causing an instant explosion that destroys the entire vehicle. Instead of heavy and complex gas generators, some modern engines use electric motors powered by lithium polymer batteries to spin their propellant pumps. These battery packs must discharge electricity at an extreme rate, emptying their entire charge in just 3 minutes. Designing these battery enclosures and high-power electronics adds another $5 million to the engine development budget. Inside the factory, the machinery is specialized and expensive. A large-scale three-dimensional metal printer capable of printing rocket engine injectors costs over $1,500,000. Autoclaves for curing carbon fiber rocket bodies run between $2 million and $4 million. Clean rooms designed for satellite integration require advanced air filtration systems that cost $300,000 to install. Then comes the regulatory wall. A startup must register with the Directorate of Defense Trade Controls for $2,500 annually to comply with international traffic in arms regulations. Law firms specializing in space regulation charge up to $1,000 per hour to draft these compliance filings. Securing an orbital launch license from the Federal Aviation Administration takes up to 2 years of paperwork and costs over $100,000 in engineering studies. This licensing process requires the startup to complete detailed environmental assessments that analyze the impact of launch noise on local nesting birds and marine life. Startups must also design a flight termination system, which is a set of explosives mounted on the rocket tanks to destroy the vehicle if it veers off course. This system must be independent of the main guidance computer and must be certified by the military range safety officers before every flight. Developing and testing these range safety systems costs over $2 million and requires dozens of test drops. Without these specific licenses, the rocket is just an expensive lawn ornament. To pay for these machines and permits, founders must pitch to venture capital firms. Seed rounds for space startups average $5 million, which barely covers the initial factory lease and basic engineering designs. The company must raise a Series A round of at least $20 million to build their first prototype engine. By the time they reach a Series C round, the startup has often raised over $150 million, diluting the founder's ownership to a small fraction of the company. Venture capital terms are strict, requiring the startup to reach specific technological milestones, like a successful engine test, within 18 months. If they miss the deadline, the funding stops, and the company collapses. This is exactly what happened to Vector Space Systems in December of the year 2019. Sequoia Capital led their funding rounds, but when they decided to pause their financial support, the startup filed for bankruptcy within 4 months. Another wave of space startups attempted to bypass traditional venture capital by merging with blank check acquisition companies in the year 2021. Companies like Astrospace and Virgin Orbit raised hundreds of millions of dollars through these public listings, but struggled to build reliable launch vehicles. Virgin Orbit launched their rockets from a modified Boeing 747 aircraft, but a single fuel filter issue caused a mission failure that drained their remaining cash. By April of the year 2023, the company filed for Chapter 11 bankruptcy and sold off its manufacturing assets for a fraction of their value. Even if the funding continues, the monthly overhead is a constant drain. The largest expense for any rocket company is engineering talent. A startup needs at least 150 specialized engineers to design the guidance software, propulsion systems, fuel tanks, and structural frames. With an average annual salary of $130,000 per engineer, the payroll alone exceeds $1,600,000 every month. Adding health benefits, payroll taxes, and recruiting fees pushes the total human resources bill past $2 million per month. The factory lease adds another $80,000 a month, while specialized software licenses for structural analysis cost $15,000 per seat annually. Insurance is another massive overhead cost. Property insurance for a rocket factory filled with explosive propellants and high-pressure tanks costs $50,000 a month. When a launch is scheduled, the company must buy third-party liability insurance, which covers up to $100 million in potential damage to government property. These launch insurance premiums cost between 5% and 12% of the rocket's total value, adding up to $500,000 per flight. In total, an active rocket startup burns through $3 million to $5 million every month before they even start building the actual rocket. Once the factory is operational, the manufacturing costs begin to accumulate. Building a single small orbital rocket costs roughly $2 million in raw materials. Carbon fiber composites for the propellant tanks cost $150 per kilogram. The copper alloys and superalloys used in the engine injectors cost thousands of dollars per build. The fuel itself is surprisingly cheap. A standard small rocket uses highly refined kerosene called RP1 and liquid oxygen. The cost of the kerosene is roughly $4 per kilogram, while liquid oxygen is only 20 cents per kilogram. A single launch requires about $15,000 worth of propellant. Instead, the cryogenic handling systems needed to keep liquid oxygen at minus 297 degrees Fahrenheit cost over $400,000 to build and maintain. To offset these costs, the company must secure commercial launch contract, a small rocket like Rocket Lab's Electron sells for approximately $7.5 million per launch. This sounds lucrative, but the startup must sign up customers years in advance. Satellite operators typically pay in installments 10% at signing, 40% at key milestones, and the remaining 50% after a successful launch. If the launch is delayed by bad weather or technical glitches, the final payment is postponed, causing a severe cash flow gap. Every time a launch is scheduled, the startup must pay range fees to the Space Force or the local spaceport for tracking and safety services. These range fees average $50,000 per launch attempt, and any weather delay forces the company to pay them again for the next day. The commercial market is also highly competitive. SpaceX offers rideshare launches where dozens of small satellites share a single large Falcon 9 rocket for as low as $300,000 per slot. This price makes it difficult for small rocket startups to compete on cost alone. They must convince customers that a dedicated launch, which drops the satellite into its exact desired orbit, is worth the premium price. Before we look at the ultimate profit margins of these launches, there is one critical mistake that destroys rocket startups. Many founders try to build their own custom valves and electronics in-house from day one. This level of vertical integration requires millions of dollars in research and years of testing for parts that could be purchased from certified aerospace suppliers for $10,000. This design trap burns through the venture capital before the rocket ever reaches the launch pad. If a company avoids this trap and achieves regular launches, the profit margins are still tight. For a $7.5 million launch, the raw manufacturing cost of the rocket is $2 million. Direct launch operations, including pad lease, range fees, tracking stations, and telemetry teams, cost $1 million. This leaves a gross profit of $4.5 million per flight. But this gross profit must cover the monthly corporate burn rate of $3 million. The company must launch at least 8 times a year just to cover their fixed overhead. At 10 launches a year, the net profit margin is only 12%. If a single launch fails, The company must halt all flights for months to conduct an investigation. During this halt, the monthly burn rate continues, while all launch revenue drops to zero. This is the high-stakes reality of the rocket business. The data shows that only a handful of private rocket companies have ever reached orbit. Most fail during the transition from engineering prototypes to manufacturing scale. The operators who survive are those who diversify their revenue. Rocket Lab, for example, generates over half of its revenue from building satellite components and space systems, not launching rockets. They realized that selling the satellites was a more stable business than building the vehicles to carry them. Owning a rocket company requires a tolerance for extreme risk, constant fundraising, public scrutiny, and razor-thin margin. The dream of orbit is alluring, but the bills must be paid in cash on Earth. A single engine injector, printed in copper and sealed in a vacuum, remains the only asset from a $50 million venture capital fund.